All right, attendance is open. If y'all want to check in on attendance, attendance should be open. This thing doesn't want to sit right today. Crackling all class. Everybody's kind of early today. Still got another minute. All right, so go ahead and get started. If you have not already done attendance, please go ahead and do that. Like we got 74 today. All right, so quick question. What do we have next time we meet? An exam, right? And it is another respondus exam, just like what you did last time. So if you need to run your practice respondus and you're trying out a new device, whatever it is, you can do that. I think a couple of people learned that the dorms are not a good place for Wi-Fi. So you might want to find a computer lab. Be a good decision, right? So please make sure that whatever device you want to use for your exam, you know it works. You know it's good, okay? And you know you're going to have a addition to your material that you'll have available during the exam. So if you go to Moodle, and you go down to our page, I'm going to put for our exam 2, oh, I thought I put it over here. Oh, here, resources for exam 2. Oh, and I should have moved it up there. Let me move it real quick. Okay, so this is what's available for exam 2. I'm sorry, it was in the wrong place. Okay, so resources available on exam 2. You have the periodic table, you have the names, the equations, the conversions. That's what you had last time. In addition to that, I added to the end of it polyatomic ions and an electronegativity chart. Okay? Any questions about that? All right. Any other exam related questions?
What's the time that it opens and closes?
It opens at our normal class time and closes at our normal class time and will be open for you to take. You have an hour to take it in. because some people have class before and after us. And so it has to be within our normal class period. So I designed the exam to take y'all about an hour. And then you have, you know, you got your little setup, you got to do all your respondus stuff, right? So all that has to fit into our normal class period. So I designed the exam to be an hour long. Okay.
I think online it said from like 12 to 5.
Yeah, but it's not, it's our normal class period, because we have people with extended time, people with, so it's not, you're open for our class period for 1 hour, our class period for 1 hour. Okay. Good. I'll go in and I don't know what y'all see. I don't know how to, I will look and see. It's only supposed to display to y'all for your class period. So maybe I've got some display setting going on, but just like last time, that's the way it was last time. That's the way it's going to be this time. Okay. Anybody else? All right. Okay. So we are going to do a really quick couple of clicker questions on a little bit of exam material, and then we're going to start chapter 5. And then at the end, hopefully we'll have a few minutes and we'll be able to do a couple of clicker questions on chapter 5, what you should have done. You had put the resource link under, oh, did I put it in the wrong place? I'll go back and check it, Jade, and make sure it goes in the right place when class is over. Okay. Oh, I need to move that. That's what I need to do. Okay, view, full screen. Okay. Make this a little bit wider, no? This way. Okay, here we go. All right, what is the name of an unbranched hydrocarbon with the formula C5H12? C5H12, an unbranched hydrocarbon. Y'all must be studying. Everybody's answering very quickly. I think we only had 75, right? I think we're only up to 74. I'll wait for the minute. Oh, 77. It's a good thing I waited. Okay. So what did you get? A hydrocarbon with an unbranched. Why is unbranched important? Why is being unbranched important in naming? Well, if I had, let's say, 1, 2, 3, 4 carbons in the chain, and then this one I took and I put on this carbon right here, would we name it the same thing? No, it would be a different name. So it's very important that you know that. So that would be pentane. That would be pentane. So you can see it in the molecular, in the Lewis structure or in the skeletal structure. Either way, it's pentane. Yes, like last time, the question is like last time, can we come in person and take the exam? Yes, you absolutely can. And there's a computer lab within spitting distance. Maybe not spitting, but pretty close. Pretty close. Okay. What is the name of the saturated, unbranched hydrocarbon with this formula? So it is a saturated and it is unbranched. Okay, y'all, 5 seconds. When you were doing this, what was a red flag for you? When you said, when this is a saturated unbranched, what does that formula look like? CnH2n, right? It's a double. The number of hydrogens is double the number of carbons. So what does that tell you this has to be? It has to be a cyclo. So I could get rid of all of these. And then all I have to know is 6 carbons. Is that hex or is that pen? It is 6. So it is hexane. So either way you could draw it, Lewis, you could draw it skeletal, but we're talking about cyclohexane. Okay? Those are things that when you're taking the exam, if you see something like that, do you have to draw it out? No. You were just told that it's saturated and unbranched. That means all it has is carbons and hydrogens, and it's a continuous chain. Either it's a long chain or it's a circle, but it's still just a chain, right? So that should speed up your exam time a little bit if you keep those things in mind. Okay. Let me fix that. Okay. So how do conformational and conformational, O-N-A-L, conformational and structural isomers different? How are they different? I'll give y'all a minute 30. Okay. All right, so when we look at this, how about A? They don't differ. Conformational and structural isomers are 2 terms for the same thing. That is not true. That is absolutely not true, right? Okay, look at C. Structural isomers represent one compound, while conformations are different compounds. No. Structural isomers represent different rotational forms of a compound, and conformations represent different compounds. What do we say about a conformation, right? You can change your body's conformation without changing yourself, right? So it's just a rotational form. A conformation is a rotation. It's just a movement, right? You can draw a, I don't know, hexane a bunch of different ways, right? You could draw it kind of curved, you could draw it straight across, but it's still hexane. How about a structural isomer? What happens in a structural isomer? You have the same molecular formula, what did we say hexane's molecular formula was? C6H. That's cyclohexane. So add 2 more, 14, right? So If you had structural isomers, they would have the same molecular formula. But do you know, unless I tell you, that that's a straight chain? C6H14, do you know if that's a straight chain unless I tell you? No, not necessarily. So you have to be careful. Conformations represent just how you orient in space, but a structural isomer is a different structure. You've moved a carbon around, it's bound to something different, right? But when you add up the number of carbons, you add up the number of hydrogens, they're going to be the same. So be careful about that, okay? All right, so B, good. Okay. All right, now we have two different compounds. What is the relationship between these two compounds? And I have to apply what we just talked about. All right, y'all. 5 seconds. Okay, so when we look at these two, what could you tell me about them? Do they have the same number of carbons? Yes. 1, 2, 3, 4, and then we have the fifth as a substituent. Now, does it matter which way I go on this one? Doesn't matter. Let's go this way. 1, 2, 3. Then I have 4 and 5 as substituents. Do they have the same molecular formula? I have C5H what? Right? Okay, so are they the same compound? If I'm looking at one substituent here and 2 substituents here, can it be the same compound? It's not the same compound, right? If I gave it this, if I named it, would I name these two the same? No, I can't, because they have 2 substituents. One has 2 and one has 1, right? So they can't be the same compound. They are different conformations of the same compound. Well, I just said they can't be the same compound, right? So they are different compounds with different formulas. We just wrote the formulas. Are the formulas different? Nope. So they must be what? Structural isomers. So they are structural isomers. Okay. All right, now let's try and name this compound using our normal IUPAC methodology. Thank goodness the air conditioning turned off. You have a little bit longer to get your answer in. Okay, at 1:30, I'm calling it. Okay, so how should we do this? Are we going to number the ring or are we going to number the side chains? Because, right, you have to kind of decide that. So the longest is going to be the ring. So where do I want to start numbering my ring? On either one can be a 1. Doesn't matter which one you pick. But now, do I want to go towards the top or do I want to number towards the bottom? I want to go to the bottom. Why? Yeah, right. We want all of our substituents to have the lowest number possible. That's right. Okay, so we have 6. So we have a ring. So this is cyclo what? Hexane. Okay, so what do we have attached to our ring? I have 2 substituents and they are both what? Methyl groups. They're both methyl groups in TH. Methyl groups. Okay, so what positions are they at? They're at 1, 3. Then what do I say? Dimethyl. Cyclohexane. 1, 3 dimethyl cyclohexane. Now, this is the thing that you have to worry about with this is what's inside of that ring. Double bond. So what changes? What part of my answer changes because I have a double bond? The hexane part. So how do I change that? Because see these double bonds? So what would I call it? Hex. So you could call it hexene or you could call it benzene. It's a benzene ring. Remember all of the functional groups and everything? So you call it 1,3-dimethyl benzene. Okay. So how do we do on that one? Yeah, see that was, y'all were going for the cyclohexane, but what you didn't notice was an ane. If it is A-N-E, what does it have to be? Carbon-carbon single bond. So be careful about that. When you're looking at those single bonds, that's the A-N-E. So look at remember your A-N-E and then your E-N-E and then your triple bond, right? And then you also have to worry about a benzene ring, okay? All right. How many more we got? Let's see. I think one more. I think this is the last one. Okay. All right, so now that you remember about double bonds and things, name this molecule. Okay, 10 seconds. Okay, so when you were looking at this, how many carbons? So what's 5? Pent. We only have 2, right? So we only have 2 choices. What do you notice about that double bond? We have one going below the double bond, and we have one going above, right? If we drew our dotted line. So what do we know about that? That must be trans. That must be trans, right? So if we go, we have trans to pentene. So what does the 2 tell us? If we go back to keep my structure, yeah. What does the 2 tell us? This is the first carbon on the double bond. It's just telling you where that double bond is, right? So look at your answer choices and eliminate the ones that you can eliminate. That's the best way to go about it. And then you're only deciding between 2, right? What would cis look like? Well, you would have to name it as cis or trans because it's a double bond. So you would have to say, do the substituents both go above the double bond, or do they both, or both below, or one above, one below? So if it's trans or cis, the substituents don't have to be, well, technically it's not really substituents. Technically it's part of the main chain. But when you analyze that carbon-carbon double bond, what you're really looking at is what's connected to those main carbons that are involved in the double bond. So we're looking at whatever's attached below the double bond and whatever's attached above the double bond. Does that make sense? Yeah? Okay. All right. So what do we got? Y'all were close. See, y'all eliminated. That's really good. Y'all eliminated A, B, and D. Just because you knew it wasn't hex, because you knew it was pent. Then you had to pick between the 2. So that was really good. Okay. So that was my little bit from next exam. So we're going to go on to chapter 5. So you should have watched sections 1, 2, and 3 from chapter 5, right? We're talking about thermodynamics and kinetics and all that kind of fun stuff, right? Okay, view, full screen. All right. Give everybody a chance to get all their papers together. I hear all the paper rustling. Okay, for our first one, when vinegar and baking soda are combined, the mixture spontaneously undergoes an endothermic reaction while releasing CO2 gas. Anybody ever done that before? Mix vinegar and baking soda? The little, the little experiment where you make the volcano, right? All right, so would the test tube feel hot or cold? So if it is endothermic, what's the definition of endothermic? Means you're going to absorb heat. So the reaction will absorb heat. So if the reaction is absorbing heat from the surroundings, where does it come from? From the surroundings, right? Would we expect our test tube to feel hot or cold? If we're absorbing heat, the opposite of absorb is to release heat, right? So if you're holding on to something and it starts absorbing your heat, how's it going to feel? It's not going to feel hot. It's going to feel cold. If the reaction is pulling heat from your hand, like you have your hand wrapped around the test tube, right? If the reaction, if heat moves from my hand into the reaction, how is my hand going to feel? My hand was a certain temperature, and some of that heat moved into my test tube. How's my hand going to feel? I'm not asking how the reaction will feel. I'm asking how my hand's going to feel. My hand's going to feel cold, right? So that's what you're going to feel if you're holding on to that test tube. The test tube is going to feel cold because the reaction is pulling your heat in order to make it go, right? So we said if it is endothermic, that means heat is entering the reaction. Well, where did it come from? It came from the surroundings. So the surroundings are going to get cold. So would the test tube feel hot or cold? It would feel cold. All right. So the next thing says, do you think this reaction would have a positive or negative value for delta G, and explain? There's a particular part of this sentence, of this little statement, that tells me the answer. I heard the answer, I heard negative. So why would you say negative? What was that? Because it is spontaneous. That was our key word right there. Spontaneous. That is by definition what delta G is. Gibbs free energy, the energy available to do work. So if delta G is 0, the reaction will go. You don't have to do anything to make it happen. Okay? So in your own words, define free energy change, or delta G. And, oh, explain your reasons. Because the reaction is spontaneous. Okay? In your own words, define free energy change, or delta G. Delta G is what? You can put it on the chat. I just said it a second ago. It's energy, so it's the amount of energy to do what? Available to do, that's right, good, from Aaron, to do work. Okay, now I want to draw your attention to something. In A, we're asking, how does delta G differ in exergonic and endergonic reactions? Is exergonic and endergonic the same thing as endothermic and exothermic? No, because here we have, in first one, we have endothermic reaction that's spontaneous, right? Well, you can have an exothermic reaction that's spontaneous. Absolutely. Whether it absorbs or releases heat does not determine spontaneity. So try to keep those terms separate. I know that they sound really similar, but you have to be careful. When you hear thermic, what should you think? Heat, right? Something's hot, something's cold, temperature, right? So that's right. That's exactly what you should be thinking. Endothermic, exothermic. Is the reaction absorbing heat, or is the reaction releasing heat? When you think exergonic and endergonic, what does it start with? The like second half of the word. Starts with the letter G for delta G, okay? So endergonic and exergonic tell you all about delta G, and delta G tells you spontaneity. Is it going to happen on its own, or does it need a push? Okay, so A, how does delta G differ in exergonic and endergonic reactions? So if we are exergonic, anybody want to take a stab? Are we going to talk about heat here? Nope, can't talk about heat. We have to talk about what? Delta G. So delta G is what? Positive or negative? I said I had a chat, but I guess not. It is negative. So if it is endergonic, delta G is positive. Now look at part B. Which is spontaneous? A reaction with a positive or negative value for delta G. So we're just going to add on to our answer. So if something is endergonic, its delta G value is negative and is therefore reaction is spontaneous or non-spontaneous? If you have extra free energy, it's going to be spontaneous, right? If you don't have enough free energy, if you have to put energy in to make it happen, it's going to be non-spontaneous. But if you have some extra left over, that's a negative delta G. So this one's going to be spontaneous. So on the other hand, if we have an endergonic reaction, delta G is positive, and the reaction is what? Non-spontaneous. And your book does this kind of jumping back and forth. Look at 3. I know I did it in the video. But now do you see how they're asking you about exothermic and endothermic? It's going to be really important to pay attention to the second half of that word to know if they're talking about heat or if they're talking about free energy. Don't make that mistake. Be very, very careful. Okay. 5.4, classify the following as exergonic or endergonic. So this is just what we were talking about. On a reaction energy diagram, let's draw one. The reactants show lower energy than the products. So when I draw this diagram, what's going to be closer to 0 on the axis? If this is 0, what's going to be closer to 0? My reactants or my products? It's always what? Reactants going to products. So I have reactants going to products because this is time on this axis. And so whenever we're progressing in a reaction, we're going reactants to products. So in A, the reactants show a lower energy than the products. So I'm going to pretend my reactants are here and my products are up here. So now I have to figure out, is my delta G positive or negative? And then I can tell if it's endergonic or exergonic. So if you start out with a small number and end up with a big number, okay, so think about it this way. Do you remember when I was saying in the videos, you were riding a bike, right? Is this, if I turn this into a hill, is this a hill you want to ride your bike on? No, what kind of a hill do you want to ride your bike on? I'm still going reactants to products. How about this one? Do you want to ride this one? Yes, right? I want to ride the one where I don't have to put a lot of work into it. This one on A, let me abbreviate it, A and B, right? On A, how hard am I going to have to pedal to get from reactant to products? I'm going to have to pedal hard. I'm going to have to put a lot of energy in. Is that going to be a spontaneous reaction? No. How about B? Is B going to be a spontaneous reaction? Right? It's easy. I might need a little push to get started, but then it's smooth sailing to go down, right? So A is going to be endergonic, right? I would have to put a lot of energy in to make that happen. Does that make sense? Okay. Okay, and then in B, right, are our products lower than our reactants? Did I draw it right? I have products lower than my reactants. That's right. So this is an easy coast down. This is nice. This is exergonic. I didn't have to expend energy. So if you kind of think about these energy diagrams as hills and you're riding your bike or roller skates or something like that, it'll make a lot more sense. Okay, let's see. We got to go to the next page. All right. Oh, give the sign of delta G for the reactions in problem 5.4. So wait, let's go back. So we have to give the sign of delta G for 5.4. So if I can get this right, come on. Okay, so for 5.4, this is what we just did. What are we going to say for 5.4? How about for A? Are we going to have a positive or a negative? This is going to be a positive delta G, right? We're endergonic. We have to have a positive delta G. And how about B? What are we going to have here? Negative. You know they're endergonic or exergonic, you can easily put those signs in for delta G. Good on that? All right, let's see. Okay, so we talked about heat. We talked about free energy. Now y'all got another symbol. I know, another one. Delta S. What does S stand for? What does S stand for? Entropy? What is entropy? Sounds super sciencey, but doesn't tell you too much. What's entropy? An easy word for entropy. Organization, right? So the more entropy something has, the more disorder it has. If you were to go take a look at my son's bedroom, let me tell you, the entropy in there is through the roof, right? I prefer my room with less entropy. I prefer a clean room. There are lots of different ways that things in our environment can be arranged. And have y'all heard that statement, the universe tends towards disorder, right? You know what it makes me think of automatically? It's Christmas lights. I know, right? But how many different ways can those Christmas lights get all tangled in the 1 year that they're up in the attic, right? There's such a mess every time you take it down. But really, there's only one way for it to be stretched out and untangled, right? So you have way more possibilities for disorder than you do for order. It's like a constant battle against fighting your son to clean his room. You know, same thing. Okay. So think about, when you think about disorder, right? I want you to think about the organization of things. So if we think about states of matter, if we think about the organization of states and matter, solids, liquids, and gases, which one do you think is more disordered? Gases. So we have disorder on this side, and we have order here, right? A solid keeps its shape. It keeps the arrangement of particles. As we go from solid to gas, we get more disorder. That makes sense? Okay. So let's look at A. It tells me I have liquid gasoline burning to form carbon dioxide. What is carbon dioxide? It's a gas. How about steam? It's a gas. It's just water vapor, right? So tell me what's happening to my I don't want to say solution, to my reaction. Liquid gasoline burning to form carbon dioxide and steam. I'm getting more random, right? So A, I'm getting more random. So if entropy, if S is disorder, should S be positive or negative? Are you gaining it or are you losing it? I'm gaining disorder, so delta S is positive. Okay, B. Cleaning up your bedroom. You're going from disorder, right, to order. So what should my sign be on delta S? Delta S is negative. Okay. C, a stick of dynamite exploding. If things are things getting more random or less random? A stick of dynamite is really a solid, right? And what happens when things explode? All you have is gas, right? All you have is gas. That's the big pal, right? So what's happening with delta S? We're going from order to disorder. So delta S is positive. Okay, so this section goes back and forth between heat, enthalpy, entropy, which is disorder, and gives free energy. So it's kind of like three big things that you have to kind of keep going in your mind all at the same time. All right, classify the following as spontaneous or non-spontaneous. Walking on a treadmill at the gym. Do you have to put energy in to get on the treadmill? Yes, you do. That's the whole point of getting on the treadmill, right? Is to put energy in. So if you're putting energy in, is that spontaneous? Is it just happening? Gosh, wouldn't that be nice, right? If we just spontaneously were on the treadmill, but it doesn't work that way. Okay, so this is non-spontaneous. Okay. A chemical reaction that requires free energy. It's requiring you to put in energy, just like it's requiring you to put in energy to get on a treadmill. Non-spontaneous. If you put a treadmill in place, a reaction that requires you to walk on a treadmill, right? It's the same thing, non-spontaneous. So for this section, I'm going to suggest you look at those extra practice problems at the back, because these problems don't take long. These problems, it's just kind of this or that, right? And so if you utilize those extra practice problems at the end of the chapter, they're really good resources for you to go back and like check yourself. Oh, did I really understand that? Okay, so now we have some practical application, right? We all know that the things we eat provide us with energy, right? And different things that we eat provide us with different amounts of energy, right? If you eat a lot of high fat foods, what's inside of those fats? Calories, right? So if we compare our three different molecules here, carbohydrates, proteins, and fats, which one is going to give us the most amount of energy per gram of food? Which one's going to give us the more energy? Fats. For every gram of fat, you're going to get 9 calories. Then carbohydrates and proteins. But the thing with carbohydrates and proteins is that proteins don't tend to be used in our bodies as energy. they tend to be used as building blocks, right? So if you eat that steak, the protein inside of that steak, your body's going to break it down and use the components inside of that steak, the protein parts of it, rather than use it for energy. It's because you need those building blocks, right? And your body can use the carbohydrates and the fats for energy. So proteins will provide you with energy. Like if you go into starvation mode, right? Let's say you go hiking, you get stranded, whatever it is, right? Your body will start breaking down your own muscle tissue so that you have energy to survive, right? So there is energy trapped inside of those protein molecules, but typically what we use the protein for is building blocks, because that's what makes up all of the proteins in our body. Okay, so this last one's a little bit of a challenge one, right? So we're taking it really practical. We're gonna have breakfast. Everybody had a good breakfast today, right? Our breakfast consists of 2 eggs. All right, let's see. So we have eggs, and we want to know how many calories in our breakfast, right? If we have eggs, we have 2 of them. I need to go up to my table and I need to figure out for each food, how much of each of the 3 categories am I going to get for this? What do you mean reaction time, Jake?
Like sugars and carbs, like it would react faster.
You do. That's why like marathoners will carb load before a race so that that energy is quickly accessible. So yes, there are times when you're looking for particular types of food. Absolutely. Okay, so we got 2 eggs. What do we say? Okay, so we got to come up here and we got to say eggs. Okay, so all of my numbers are for 2. All of the numbers in the table are for 1. I need it for 2. So I'm going to look at my carbs. I'm going to look at my protein. I'm going to look at my fat. Y'all are going to have to help me so I don't have to scroll back and forth. Okay. So I want to do each of my foods, and then I'm going to do carbs, and then I'm going to do protein, and then I'm going to do fat. Okay, so 2 eggs. I'm going to do 2 times whatever my carbs were. What are my carbs? 0.6 for a total of 1.2. Okay, now I need 2 of my protein. What do I get in protein from an egg? 6.07. So that gives me 12.14. My fat, 2 times and that gives me 11.16. Okay. So I want to know how many calories would be found in breakfast, right? So that's just my eggs. Is that my whole breakfast? Nope. I had something else for breakfast. What did I have? I had 2 pieces of toast. So I had toast, and I had 2 of them. Is the table 2 pieces of toast or 1 piece of toast? Oh, it's 1 bread, right? So we got to multiply all that times 2. So if, whoop, oh, that is brilliant. I just learned that the back of the pen will erase and the front of the pen will write. Oh, my day just got great. Okay, so toast, 2. How many carbs in a slice of bread? Should be a lot, right? 14.1. Okay, so that gives me a total of 28.2. Then my protein, shouldn't be too much protein. 2 point what? 2.4. Okay, so 4.8, not 8.4. 4.8, okay. And then fat, 2 times 1.8, okay. So, but what did I put in my toast? Because what good is toast if you don't have a little butter on it, right? Okay, so what do we do? 1 tablespoon of butter. So we got to come up here. We got to find our butter, 1 tablespoon of butter. So we don't have to multiply by anything because we're doing the, right? 1 tablespoon, 1 tablespoon. The amounts match. Okay. So this is my butter. Okay, so my butter, it said 0.008. Protein, and then fat. Should be a lot of fat. 11.5. Okay, so, oh, but we're not done yet, right? I didn't know this problem was going to get so long. I had some OJ. How much OJ did I have? 6 fluid ounces. So I need to go back up to my table and find my orange juice. Uh-oh. What do you notice? My units aren't the same. I'm given in the table in cups, and I only know that I drank it in ounces. So what am I going to do first? Trying to extend the page so I get a little bit more room. There we go. Okay. So I need to do a conversion. If I have 6 fluid ounces, anybody have their book? They know they can find the conversion? Anybody? I'll tell you, in 1 cup, in 1 ounce, you have, let me do that. In 1 ounce, you have 0.125 cups. So what do you get? How many cups? How many? 0.75 cups. Okay, so now what do I have to do? I have to multiply 0.75 times whatever my OJ was. Where's my OJ? Here. So my carbs are 27. And then I need to do 0.75 and 0.75. So what do I have for protein? Not much. 2. And then fat, 0. Okay. Which I didn't leave myself room. So if you multiply 0.75 times 27, you should get 20.25. And then I get 1.5 here. And then I get 0. Right? Okay. I've done all this work. Do I have my final answer yet? No, why not? Well, I need to add them up, right? So I get my total number of carbs. So somebody tally up carbs. So we're looking at, we have 1.2, 28.2, 0.008, and 20.25. Add those up. So our total, so this last column is going to be our total. 49, oh, y'all are so awesome in the chat. 658. Okay. Is that what everybody else got? That doesn't sound like enough. Is that enough? 20, 40? Yeah, okay. All right, how about the next column? 1.5 plus 1.5 plus 0.12 plus 4.8 plus 12.14. 18.56. Okay, and then our last column is 0, 11.5, 1.8, and 11.6. $24.46. Oh, I like the chat for this. That's nice. All right. Am I done? Did I answer my question? I tell you, this is like a marathon problem. I know my total carbs, I know my total protein, and I know my total fat, right? This is carb, protein, fat. What did the question ask me for? Calories. Now what do I have to do? I have to convert it. I have to convert from carbs to calories. So how do I do that? I'm going to extend my page. So let's do carbs. Let me see. I have 49.658 carbs. How do I convert from carbs to calories? Well, think about it, right? If you have different foods, each gram of a different food is going to be worth a different amount of calories. You could do it for proteins and carbs. I'll give it to you there. You could do it for protein and carbs, but fats have a different number of grams per calorie or calories per gram, however you want to think about it, right? And that's what these are. All of these totals are grams of each. Add the calories that are on the chart. What calories that are on the chart? Yeah, but you could go about it that way. You could. Okay, so let's come down. Let's finish down here. So how many calories per gram of carb? In 1 gram of carb, what do we get? How many? What was? I can't hear you. 4. Okay, 4 calories. So what do you get? And I'll set it up over here for proteins, right? Proteins. We said proteins were also 4 calories per carb. Per carb. Haha, no. Per protein. And then the same thing down here, 24.46 grams of fat this time. I'm getting too low on the page. It doesn't like it. But fat, be careful. What is fat? 9 calories in 1 gram of fat. So what do we get for each one? Y'all gave me I think y'all gave me the total. So protein, somebody says protein is 74.24. Okay. How about carbs or fat? Put it in the chat, y'all. How many carbs? Somebody said carbs. Okay, carbs are 198.632 calories, and then 220.14 calories of fat. So now what can I do? I'm gonna add them all up, and this is all the calories that I've consumed in my measly old breakfast, right? You didn't think it was bad until you started adding it all up. We always feel like that. So what do you get for a total? Just do the simple addition of the 3. You get 493.012. This is calories. And remember, this is the big C calories, right? The nutritional calories. Because remember, I don't know what chapter that was. We converted between little c and big C, right? The little c is energy, the big C is nutritional. Okay? What was what? Oh yeah, so we need to worry about significant figures. So let's go up. What were our significant figures off of the table? I wouldn't, almost there it would be like 1 significant figure because you're given 6 fluid ounces. I hate things that are 1 significant figure. So let's just give it to 2 significant figures. Let's just give it to 2. So what would you say? 490 calories. 490 calories. On the exam, I'll be good. I'm using the book's problems here. I mean, I try very hard to never give y'all anything that is 1 significant figure. And they're going to be multiple choice. And honestly, I'm not testing you on straight significant figures anymore. Not again until the final exam. So I'm not going to give you a math problem and all the answers are the same, except they're different significant figures. unless you might see that on the final exam. But you know what I mean? Yeah. Okay. I know, it's kind of big, but it kind of makes you think about all the things that you eat, you know? All right. Moving on. Chemical reactions and kinetics. All right, how much time? What time is it? No. All right. So, kinetics. Kinetics is all about how quickly something happens, right? When you think about kinetics, think about the speed of things happening, right? And when I think about chemical reactions, I like to think about cars. So you heard me talk about that a lot on the videos. I equated them a lot of times to cars. So in order for a reaction to go, molecules have to get close enough to one another that they actually hit each other, that they actually collide. So that's why I think about it with cars, and I think about the cars actually hitting and impacting one another, right? So when you kind of think about that, you can use that as an analogy to answer some of these questions, right? Like what happens if you increase the temperature? Well, tell me about molecules and temperature. What happens when you increase temperature? What do our molecules do? They move faster. Temperature is a measure of how fast molecules are moving. It's just their speed. So if you have a bunch of cars on the road and everybody hits the gas, what's more likely to happen? A collision, right? The faster cars are going on the highway, the more likely they are to run into one another. Same thing with molecules. So if you kind of think of them in that terms, it should kind of help you. Okay. So let's see, we did 5.13, 5.14. Describe the activation energy for a chemical reaction. I thought it said we had a chat. Am I far down? Oh yeah. Okay. All right. So when you write that little activation energy, you got to think about your reactants going to products, right? If we said, here I am, and here I want to be, right? I'm in the reactants. I'm up high at the top of the hill. I'm sitting on my bike. Do you just go? Or do you have to pedal just a little bit? Or have somebody kind of give you a little shove, right? You have to get that little shove to get your momentum going. Well, that's exactly what happens in a chemical reaction. We like to think, oh, I can just connect the dots like that, but you can't. That's not what really happens in a chemical reaction. What really happens in a chemical reaction is we have to go through this little intermediate stage, and then we can go down to our products. And so this little bit of energy right here that you put in, so from here to here, the energy that you put in right there is the activation energy. So did you have to put in a lot for this kind of a reaction that we drew right here? No, just a little bit, right? But what if I want to make this reaction go faster? I lower my activation energy. So here's my original reaction, right? I had to go through that little bump of activation energy. Well, I want this reaction to be easier. I don't even want to push the pedals on my bike very hard, right? So what I'm going to do is I'm going to lower my activation energy. So I'm still going to start at the same place. I'm still going to finish at the same place. But now look how much energy I have to put in, right? From here to here. It's even less. So how can you make a reaction go faster? You can add a catalyst. And that's what we did from going from like A to B. In B, we added a catalyst. So tell me, what does a catalyst do? How does adding a catalyst increase the rate of a chemical reaction? It just lowered, I guess I should write it out. It lowered the activation energy. right? Because what is that activation energy? It's that little bit of energy we have to overcome in order to progress from reactants to products. And sometimes it's more than a little. In our example right here, it's only a little. So the activation energy is the energy required to progress from reactants to products. Right, you got to overcome that little bit of an energy barrier. And now your reaction can go. You can coast down the hill. So would you consider this a fast chemical reaction, you think, or a slow? If you're riding your bike and you take this hill, are you going to be going fast or are you going to be going slow? When you go down this hill, you're going to be booking it or are you going to be working hard to get there? This is going to be a fast one. This is going to be fast, right? You put your feet up and the wind goes and blows your hair back, right? Okay, so how about a slow chemical reaction? What do you think is going to be different about a slow chemical reaction? It's going to have a high activation energy. Could we draw that? What do you think that's going to look like? So we start low and we have to go high. Oh, right? So we can't really just connect the dots. We want to just connect the dots. But what happens is you actually kind of go up a little bit higher. And so your activation energy is right here to right here. So that's a lot of activation energy that you have to put in order to make this reaction go. So it's going to go slowly. I promise you, climbing up the hill is going to take more time than going down the hill. Okay, so you're lucky enough you have an enzyme that is going to lower your activation energy, right? That's what an enzyme or a catalyst does. So how does a catalyst do that? Right? It kind of reaches out and it grabs those molecules that are participating in the chemical reaction and orients them so that they can properly interact. So there's a name for the part of the catalyst or the enzyme that can fit our reactant molecules. Well, so the reactant molecules are the substrate, but there's a place on the enzyme. It's called the active site. The active site. So like if the analogy is I'm the enzyme, right? My hands can reach out and grab whatever molecules, right? And smash them together in the right orientation. So my hands are going to be the active sites, right? It's not all of me. It's not all of the enzyme. It's just a part of me that can grab those reactant molecules and pull them in. Okay. All right. Now, we want to know how conditions changing are going to affect our rate of reaction. So is it going to speed it up? Is it going to slow it down? So what if we have a metal surface that two reactions can basically rest on in order to interact with one another? You're providing them with a surface that's going to promote interaction. So what's going to happen? you're going to increase the rate, because this is a metal surface can actually be a catalyst. C-A-T-A-L-Y, catalyst. Not all catalysts are, the one that I was describing is kind of like what happens in our cells, in our bodies, right? That's the most common kind of catalyst that we think about, but it's not the only one. You can have surfaces that just provide a place for the reactant molecules to hang out together and to make that reaction happen. Okay? All right, decreasing the amount of one of the reactants. So this is how I think about the cars, right? If I start out with a certain number of cars on the road and I take away half of them, are they more likely to have accidents or less likely to have accidents? They're less likely to have accidents. What's an accident? A collision. In order to get reactions to go, you have to have collisions. So if I take away some of the reactants, I'm going to have fewer collisions. If I have fewer collisions, I'm going to decrease collisions. If I decrease collisions, what's going to happen? I'm going to decrease my rate. All right, caramelizing onions on a medium-high stove setting versus a low. So in this case, we're going from low to high temperature. What's going to happen? We're going to increase our collisions, right? Because things are flying around super fast, right? And so that is going to increase our rate of the reaction. Okay. I think y'all are pretty good on that. Sounded very confident, right? Okay, so I think what I'm going to do is I'm going to stop, because we'll end up getting caught on section 3, and I'll pick up on section 3 next week. But now listen, before you walk out of here, exam tomorrow on Respondus. Thursday, next class period, Thursday. After the exam on Thursday, you're going to have 3 sections to watch in chapter 5. So make sure that, I know like you got to mentally, I finished my exam, I need a deep breath, right? But when you come in on Tuesday, you need to have finished watching all of chapter 5. And we're going to finish the in-class problems on Tuesday. If you have any questions, come let me know. Please test out your equipment for your Respondus exam.
You know the question where it asks if the proteins and like carbohydrates.
Yeah.
Do you have any case like where we would have figure out like
No, like okay, I want to do whatever it is. What meal should I eat? No.
I was just asking.
No, I just, like sometimes, I don't know, I feel like y'all just kind of want to know a little bit more because it pertains to real life.
Yeah, like
So I
deal
kind of
with
start,
this every day being an option.
and there you go, so everybody else kind of gets a glimpse into what you have to think about, right?
Absolutely. Yes, ma'am.
All right, yeah, no problem. On exam 3. On exam 3, yes ma'am. What's that? Okay. 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 So
I don't understand how can you like intermolecular non-polar and polar. Okay, like a non-polar bond and then a polar bond and then a B.
okay.
It's really confusing. I'm really
So you're asking about, you want to know how you can have a molecule that is nonpolar with polar bonds?
with it being polar covalent.
Well, all polar bonds are covalent by definition.
Yes.
So either the bond is nonpolar covalent or polar covalent.
I don't get it.
Okay, so if you have carbon,
Uh-huh.
CF4,
Uh-huh.
So remember, fluorine is
Correct.
the floozy, right? She wants all those electrons.
Correct.
So we know that there are 2 electrons that are shared between carbon and fluorine,
Correct.
right? But those 2 electrons don't spend time equally with fluorine and chlorine. They don't.
This fluorine takes more of the time.
Correct. So fluorine hogs them,
Okay.
right? So we're going to call them bonds. We're going to do this, and I'm not drawing fluorine's lone pairs just because. Okay. So fluorine, do this right.
Would go to fluorine.
To fluorine, and we'd have a plus sign there.
Correct.
It would go to fluorine, we'll have a plus sign there.
Correct.
To fluorine, we have a plus sign there. To fluorine, we have a plus sign there.
Correct.
Ever done in physics?
At LSU, but I just.
You remember vectors?
Yes. Okay.
Okay, all the vectors cancel out.
Okay.
So like, let's just say you
So
only
then
had
it would
2.
be, it's polar, right?
It's polar bond,
But it's not.
but it is a non-polar molecule. So these are polar bonds.
That's what she was talking about.
Yeah,
That's
polar
exactly what she was talking about.
bonds. This is a non-polar molecule. The reason it's a non-polar molecule is because it is symmetric.
It's almost like reducing.
Yes. So it's almost easier to think about it if you had a linear molecule, right? Let's say we had 1 atom in the middle, and then I had two on the other side, right? So I'm sharing 1 electron with each of these neighboring atoms. And so if I look at this bond, right? Let's say it's fluorine. Oh, she's just hogging those electrons, right? So electrons are over there. So over there is negative. And if that's all it was, I'd be leaning over, right? But guess what? I got another atom over here. And this atom is pulling my electrons to them.
Correct.
So now I'm balanced.
You're in the middle. That makes sense. Okay. Now, what if like it's like you have like a different atom on the one side?
Oh, then it's no longer polar. So what if I had hydrogen here? So now this bond is non-polar.
Correct.
So now this molecule has an overall polarity going that way.
Which means that it would be a polar bond.
No, polar molecule.
Not all polar bonds because that's non-polar.
Right. Okay. So look at it this way. Right here I am. I'm sharing my electrons with these 2 atoms, and they're both pulling me equally. Now, I change partners, and this one is happy to share perfectly nicely. Right? So they're only pulling on me a little bit. What's going to happen to me? I'm going to go this way.
Yes. Okay. That makes sense. Okay. That helps. If you look at it like that, like in a silly way, that helps.
You look at yeah, because I'm not. It's like a balancing act.
That works. Okay.
If we ever need to schedule a time with you, are you available?
I'm available. So in Moodle, right? Oh, I need to end this. This is going to be so long. Let me end this. End meeting.